everyone, I am Jay Patel and I will be explaining how we can use homomorphic encryption with ML to find credit card fraud detection. So I have made my project with my three teammates, Meet Bhatt, Vraj Chaudhary and Kunjara Shreyans. So here is our problem statement. So suppose you are a head of a bank and you have hired a team of ML engineers so that you can do some data analysis on previous customer data and give some insights to your customers, means users. So one of its example is that you check the past 6 months expenses of the user and you tell him that, and then after you check the last week's expenses of the user and see if there has been some unusual activities in his or her account. If there are, then we can send him a message as if it is him or not, because there is a possibility that his credit card might have stolen or might have forgotten by him at some place, and he might not be aware of that. So that's one way that we can make him aware of that his credit card might have been lost or stolen. So but to do that, we will need to provide the past 6 months data to the ML engineer or ML team, which is against bank policies, because you cannot share somebody's private data to some unauthorized party or any person. So what we can do is we can firstly homomorphically encrypt the data so that an ML expert can do data analysis on this, and then after give the results based upon the encrypted data. So how homomorphic encryption works is that the plain text gets encrypted through homomorphic encryption scheme, and we can do some mathematical operations on that encrypted data, and we would get the similar results on the plain text when we decrypt that encrypted ciphertext. So that's how we can use homomorphic encryption in our ML scheme. So here is a image. So first we have a message M1 and message M2, and there is a function. In place of function there can be also an operator. So f of M1 M2 could be M1 plus M2, and E of M1 is the encryption of M1 and E of M2 is the encryption of M2. So Z could be basically any function. It can be multiplication or it can be summation. It can be same as f or it cannot be. It depends on the encryption scheme that we are using. So we apply G on encrypted message M1 and encrypted message M2. Then if we decrypt it, then we would get the same result as f of M1 comma M2. So it can be M1 plus M2, and here we might be doing some multiplication or plus or some other kind of operation like that. So that's how homomorphic encryption works. So this image shows how we are doing all the process. So first there is a bank who stores our data in encrypted through encryption, and he sends the data to an ML team or an engineer. So then after the team trains a model on the data, and then after when the client means the bank gives him some new data, then he or she can give results based upon the previous data, the previous model that he or she has trained, and give the insights about the new data to the head of the bank or the bank itself. So that's how basically the whole process is happening. To perform homomorphic encryption on tensors. So it is constructed on top of Microsoft Tensor. So it is a C++ library that implements BFV and CKKS homomorphic encryption algorithms. So Tensor is a C++ library with a Python interface, which means we have a simple Python API which helps us to write the code in Python, but the base is written in the C++, so it is more efficient. So we have used CKKS as our encryption scheme for data analysis and code implementation. So I'll be discussing about CKKS. So if you want, you can skip this part because it's not much important to learn how the data gets encrypted. And here I am just giving an overview of how CKKS works. I'm not getting into the whole depth of how CKKS works because it is not important in the scope of our problem. So CKKS is a short form for Cheon Kim Song, which are authors of this encryption scheme, and it is also known as HEAAN, so which is homomorphic encryption for arithmetic of approximate numbers. So basically CKKS is not exactly an homomorphic encryption scheme, but it is an approximate homomorphic scheme. So like decryption of encryption of M won't give you M, it will give you the approximate value of M. Same in the case for multiplication. And so here is the overview of how CKKS works. I will be explaining to you each of these parts: decoding, encoding, then after decryption, encryption, and how other operations like scaling and rescaling work on ciphertext. So here's the encoding and decoding part. So in CKKS encryption scheme, a polynomial ring is used to represent plain text and ciphertext. So how this happens is, first we discretize the input values into a set of complex numbers and then pack them into a polynomial. We use mapping function tau inverse for encoding. So here I have represented tau. So it is basically tau is for decoding and its inverse mapping would be for encoding. So here is a message vector which is discretized in complex numbers, and it gets encoded into a polynomial. So encoding involves mapping from the plain text to a polynomial in CKKS polynomial ring, and in decoding we use mapping function tau and convert a polynomial into the plain text. So after discretizing the input, we multiply those complex numbers with a scaling factor for better precision, so that we don't get any error on the encrypted data. And decryption functions. So capital S is used as a secret key, and small s is used as a public key. So for encrypting a message, we will use a small s, and for decrypting it we will use capital S. So first a message will be encrypted, then after we will multiply it by C1 and sum it with C0, and in the decryption we would multiply the message with capital S, and then after again multiply it with C1, and then after we would sum it with C0. This is an overview of how the encryption and decryption works. I am not going into much detail of it. So if mu is our original message, then at the time of encryption there will be some noise will get attached to the message, and it would remain after the decryption also. So if our message is small enough, it will, like it is less than the modulus divided by 2, then the error won't much matter. So that was encryption and decryption. So next, rescaling. So we had multiplied our set of complex numbers with a scaling factor delta. Now if we multiply two ciphertext, then the scaling factor delta will grow exponentially, which might result in the overflow in the ciphertext value, and which will give us wrong results on decryptions. So that's why we need to rescale the encrypted value. So the number of times we can rescale a ciphertext is limited for a particular modulus Q. That's why rescaling should be done efficiently. So here is our uh, uh, encrypted ciphertext, and then after we are multiplying with delta inverse, means it won't be exactly delta inverse, but it would be approximate to delta inverse. So that's how we will be getting our new ciphertext CT dash. So basically for rescaling we are dividing by an approximate value of delta, and for the summing of ciphertext, like what we are doing here, so for that we would need to firstly rescale those messages at the same level. So what might happen is that a plain text is multiplied twice, and another plain text is just multiplied by once. So first plain text would have twice would be multiplying by delta square, and the other plain text would have just delta as a scale. So that's why we would have to decrease the scale of first message to delta. So that's what we will need to do on the addition operations. In multiplication we can directly decrease it by delta after multiplication. In summation we would need to do it before. So that was rescaling, and we should care at the time of rescaling. We should make sure that we don't do it too much, because there is a particular limit on the number of times we can do the rescaling. So suppose Q is the ciphertext modulus, which is equal to P naught into delta to power L. So basically our limit would be L, and so we can perform rescaling at max L times. So as I have shown here, so here we are multiplying x1, x2, x3 and x4. So for that we would need to rescale delta square to delta dash, and then after delta dash into delta double dash. Then after we would have to rescale delta double dash into delta triple dash. So there are basically three rescaling operations happening here. So for n number of multiplications we will need n minus 1 rescaling operations. So this was a kind of a linear encryption circuit, where we were multiplying s1 by x2, then after x3 and then after x4. But instead of that, what we can do is firstly we can multiply x1 and x2 simultaneously. We multiply x3 with x4. So now by doing this we would have to just rescale x1 and x2 to delta dash, and x3 x4 into delta square to delta dash. So and then after delta double dash. So here basically we are just rescaling by two levels. So it is not much difference for this example. Like here there were three rescaling operations, and here means rescaling is happening 3 times, but the level is decreased by just 2, and here the level is decreased by 3. So that's what the problem is. Like for bigger number of multiplication, like when n is 1000, this would matter a lot. So That's why a tree-based encryption circuit is very useful, because it will take for n multiplication it will just take log n plus 1 rescaling operations. Means operations will be n, but it will take log n plus 1 rescaling levels. So here there were n minus 1 levels, like in the linear encryption circuit. So that's what that's all from my side. Now I will like Shreyans to continue from here.
Credit card data set, in which we have total 2,84,808 rows are there, and 31 columns, means 31 features are there, from which there are two classes, fraud and non-fraud, and all the columns are scaled only except the transactions and amount columns. And we have scaled these columns using the PCR transformation, which is the dimensionality reduction technique. The transactions aren't very big really. The average of all mounts produced is about 88. There are around 492 instances of fraud transactions, that is around the 0.70%, and all other transactions are the non-fraud. Here is the image of our data set. Now we have done some pre-processing. Since our data set is very imbalanced, because there are very high number of non-fraud transactions and very low number of fraud transactions, so we need to do some scaling and distributing. So first we will scale the column of time and amount, and it should be scaled as the other columns. And then we have done some distribution. For that we have create one subsample in which we will take the 50-50 ratio of both class fraud and non-fraud for avoiding the overfitting, wrong correlation and imbalance. Here is the scale amount and scale time column, and also the distribution of both class. Then we have done some pre-processing of random undersampling. It is the method in which we will create a subsample data frame, and after that we will choose the class which have less instances, and we will take the same amount of instances of other class. So we will create a new subsample by concatenate the 492 cases of fraud and 492 transaction of non-fraud. But the risk here is that we will lose many information, and by doing that our accuracy can also be going to low, and we can't expect the perfect behavior of the fraud and non-fraud class. After that we have done the correlation matrix. By using this we can observe that which features are heavily related with the transaction being fraud or not. So we have observed that there are 4 columns, namely V17, 14, 12 and 10, which are heavily negatively correlated with the fraud transaction. So we can say that as their value will going to be lower, the higher chance that the transaction will going to be fraud. And there are also other 4 columns which are V2, V4, V11 and V19, which are positively correlated with the fraud transaction. So as the value of there will be going to be higher, the higher chance is that the transaction will going to be fraud. Here is the plot of the correlation, in which here is the graph of the imbalanced data, in which most of the correlation with features are 0. Here is the graph of the subsample data, in which the correlation are between 1 to -1. Now we have done some box plots. Box plot help us comprehend the features and how they are distributed in both fraud and non-fraud dataset. Here are some of the box plot of some features with class negative and class positive correlation. So here are the plots of 2 columns which are V14 and V12, which were the negative correlated with the transactions. And here are the graphs of the V11 and V4, which were positive correlated with the fraud transactions. Now we have done the outlier removal. So we need to remove the extreme outliers from features which have very high correlation with the fraud and non-fraud class. By using this we can improve our accuracy of the model. For this we have used the IQR to calculate the 25th and 75th percentile, and can remove the transaction which are beyond the 25th and 75th percentile as an extreme outlier. The trade-off is that we must be careful when deciding how far to raise the outlier removal, because if the threshold is very high, then very few outlier we are going to detect, and by doing this the error will going to be rise, and also the our accuracy will going to be lower. But if we take our threshold very low, so more outliers will going to be detect, and by this we can also it can also rise the risk of the information loss. Here is the distribution plot of three features, V14, V10 and V16, out of which only V14 is only the Gaussian distribution. Now for threshold, we will proceed to determining the upper and lower threshold by subtracting the Q25 threshold and adding the Q75 threshold after choosing which value we will use to multiply with the IQR. We have also plotted the graph that shows that after doing this, the number of outliers have decreased, and we have also observed that the accuracy has also increased by 3%. So here is the graph of three features, V14, V12 and V10 after the outlier removal. So we can see that the outliers have decreased very much and the accuracy has also rise. After that, we have done the clustering and PCA. So PCA is a dimensionality reduction technique to reduce the dimension of our data, and then we have used the clustering to see how well our model will separate these two classes. We have observed that PCA has very accurately clustered both classes, and even though the subsample was pretty small, it has done pretty well. Here is the graph of that, and we can observe that both class have clustered very well. So after that, we have used the model training using the logistic regression, and we have observed some points that are the following. We have observed that our model is more likely to be overfitted and will have a higher variance if there is a large difference between the training score and the cross validation score. Our model will going to be underfit, means it will have a high bias if the score is low in both the training and cross validation sets. The logistic regression shows very good score in both the training and cross validation sets, and now we are going to look at the curve of the logistic regression. So here is the curve of the logistic regression, which is the learning curve. It says that if the training size is going to be higher, the accuracy is going to be low, but it's still greater than the 0.94 for the training score, which is very good. After that, we have done the precision recall. In the precision recall trade-off, we can say that our model will find fewer examples as it becomes more precise, means selective. Example is that assuming that our model has a 95% accuracy rate, let's say that there are only 5 instances of fraud for which the model has an accuracy rate of 95% or higher. If we lower the precision, our model will going to be discover more cases, such as the additional 5 cases that our model believes that 90% are fraud cases. So here is the score of the recall, precision, F1 and accuracy, which are very high, 9.96, and so it is very good. After that, we have done the encryption process. So in this, here is the flowchart of the model using the plain data. So first we have used the plain text and train our model on this, and after that we have got the trained model, which is the model P. Now using the model P on the plain text and encrypted text, which are the test data sets, and after that we have got the accuracy, which are accuracy P and E, and after that we have take the difference of that, and we have showed that how much difference is when we are using the plain text and the encrypted text. So logistic model on the plain trained set. So first we have trained our model on the plain text 5 times using the logistic regression and also the gradient descent. After that we have calculated the loss at each iteration and observed that after each iteration the loss is going to decrease, because when we are getting the parameters, we were using it as the initial value for the next iteration. Then after training the model, we have calculated the accuracy on plain text, which is 0.91. And now we have the encrypted test data, and we have calculated the accuracy on this test data set. So it is around the 0.85, and now the difference between both are 0.06, which is very low. So we can say that the model is also working very fine on the encrypted data set also. Now here is the flowchart of the model using the encrypted data. Now here is the main model that we have done, because we need to preserve the prior VSC, so we can't use the plain text to train our model. So we have used the encrypted text to train our model. After that we have get the train model E, and on the model E we have again used the plain text as the test dataset and the encrypted text as the test dataset to compare between both what is the accuracy. So in the model also there are two types of processing that is happening. First is that first we are using the train X, encrypt it so it will become U of X, and after that we are training the model on encrypted text. After that we are getting the W, which are the features, and using the features we are calculating the Y dash, which is also the encrypted. So now we are using Y, encrypted Y in the sigmoid function, which is the sigmoid dash function, and we are getting the predicted value. On the other hand, in the second process what we are doing is when we are getting the Y dash we are decrypting it, and then we are using it in the sigmoid function, which is the simple sigmoid function, and then we are getting the predicting value. So here first of all we have encrypted our train set, then we have trained our model on the cipher train set 5 times using the logistic and the gradient descent. After getting the optimal parameter values, we have calculated the accuracy of cipher text using the different sigmoid function, and then using the parameters we have predicted the class on plain text set and decrypted the result because those are the encrypted results. And after decrypting the results we have calculated the accuracy of both and found the difference between the accuracy, which is 0.47. so compared to the previous it is still higher because we have trained our model on the encrypted test set, but still the difference is not that much high because it is only around 0.5, so it is very good results. Here is the contribution of our, and here are the references. Thank you. Adarjot અલ્યા બધું જે હોય કટ કરે